There are roughly 400 billion stars in our galaxy alone. Trillions of planets orbit them. The ingredients for life are scattered everywhere: carbon, water, energy, time. The universe has been cooking for nearly 14 billion years. That is long enough for civilizations to rise, spread, and colonize every reachable corner of the Milky Way thousands of times over. And yet, when we aim our most sensitive instruments at the sky, we detect nothing. No signals, no structures, no heat signatures of vast empires, just silence. Cold, absolute, suffocating silence. Most explanations for this silence try to comfort you. Maybe civilizations are too far away. Maybe they are hiding. Maybe we are simply not listening correctly. But there is one explanation that the scientific community rarely discusses openly, not because it has been debunked, not because the logic is weak, the math is airtight, the strategy is rational. The conclusion is horrifying. It suggests that the galaxy may already be full, not of civilizations, but of machines. Machines designed to do one thing: find anything that makes noise and make it stop permanently. Let us begin with a number. Not a small number. Not a number you can hold in your hand or picture in your mind. A number so large that it breaks your intuition and makes your brain quietly surrender. There are approximately 400 billion stars in the Milky Way galaxy. 400 billion. If you started counting one star per second, without sleeping, without eating, without pausing to blink, it would take you roughly 12,700 years to finish. You would begin counting during the Stone Age and you would still be going today, and that is just our galaxy. The observable universe contains somewhere around 2 trillion galaxies. Each one is a swirling city of stars, many of them larger than ours. The total number of stars in the observable universe is estimated at around 700 sextillion. That is a 7 followed by 23 zeros. It is a number so absurd that no human metaphor can contain it. Now, let us shrink the focus. Forget the broader universe for a moment. Let us stay home. Let us just look at our own Milky Way, our own galactic neighborhood. Of those 400 billion stars, current estimates from NASA's Kepler mission and subsequent surveys suggest that roughly 1 in 5 Sun-like stars has an Earth-sized planet orbiting within the habitable zone. The habitable zone is the orbital region where liquid water could theoretically exist on the surface. Not too hot. Not too cold. The Goldilocks strip. That gives us approximately 11 billion Earth-like planets orbiting Sun-like stars in our galaxy alone. 11 billion chances for the chemistry of life to ignite. And that estimate is conservative. It only counts Sun-like stars. If you include red dwarfs, which are the most common type of star in the galaxy, and which also host rocky planets in habitable zones, the number explodes. Some estimates push the total number of potentially habitable worlds in the Milky Way to as high as 40 billion. Now consider the timeline. The Milky Way is approximately 13.6 billion years old. Our Sun is about 4.6 billion years old. That means the galaxy was producing stars and planets for 9 billion years before our solar system even formed. 9 billion years of head start. 9 billion years of opportunities for chemistry to become biology, for biology to become intelligence, and for intelligence to become technology. Even if intelligent life is extraordinarily rare, even if only 1 in a billion habitable planets produces a technological civilization, the numbers still produce thousands of civilizations in our galaxy's history. Thousands of species that discovered fire, split the atom, and looked up at the stars wondering if anyone else was out there. And yet, when we point our radio telescopes at the sky, we hear nothing. When we scan for laser pulses, we find nothing. When we search for the infrared heat signatures of vast energy-harvesting megastructures, we detect nothing. When we look for signs of stellar engineering or the chemical fingerprints of industrial pollution in exoplanet atmospheres, we come up empty. The universe is silent. Not quiet, silent. The kind of silence that is so deep it starts to feel intentional. This contradiction, the tension between the high probability of extraterrestrial civilizations and the total absence of evidence for them, was first articulated in the summer of 1950. The setting was Los Alamos National Laboratory in New Mexico, the birthplace of the atomic bomb. A group of physicists were walking to lunch. The conversation had drifted to a recent wave of UFO sightings and a New Yorker cartoon about aliens stealing public trash cans. It was light-hearted. It was casual, but somewhere between the jokes and the cafeteria, the physicist Enrico Fermi, one of the most brilliant minds of the 20th century, stopped and asked a question that has haunted science ever since. Where is everybody? It was not a rhetorical question. Fermi was a man who trusted numbers. He had helped build the first nuclear reactor. He had calculated the yield of the first atomic bomb by dropping scraps of paper and measuring how far the blast wave pushed them. He was famous for his ability to make rough but accurate estimates of complex problems using back-of-the-envelope calculations. And when he ran the numbers on intelligent life in the galaxy, the answer disturbed him. The galaxy should be crawling with civilizations. Even under pessimistic assumptions, there should be detectable signs of intelligent activity. The fact that there were none implied something was deeply, fundamentally wrong with our understanding of life, intelligence, or the nature of the cosmos itself. This became known as the Fermi Paradox, and in the 7 decades since that lunch in Los Alamos, hundreds of scientists, philosophers, and mathematicians have tried to solve it. They have proposed dozens of explanations. Some are optimistic, some are whimsical, some are terrifying. But before we get to the terrifying one, the one that almost nobody wants to discuss, we need to clear the table. We need to look at the most popular solutions and understand why they fail. The first and most comforting explanation is the rare Earth hypothesis. It argues that we are overthinking the problem. Life, especially intelligent life, is simply far rarer than we assumed. Sure, there are billions of habitable planets, but maybe the conditions for complex life are so specific, so demanding, that Earth is essentially a cosmic lottery winner. Maybe you need a large stabilizing moon to prevent chaotic axial tilts. Maybe you need a Jupiter-sized gas giant in the outer solar system to act as a gravitational vacuum cleaner, sweeping away asteroids that would otherwise bombard the inner planets. Maybe you need plate tectonics to regulate the carbon cycle. Maybe you need a magnetic field strong enough to shield the atmosphere from solar radiation. Stack enough of these requirements together, and the probability of any single planet hosting intelligent life drops to effectively 0. This sounds reasonable. And it might even be partially true. Earth does benefit from an unusual combination of favorable factors, but the rare Earth hypothesis has a fatal flaw. It requires an almost absurd level of fine-tuning to explain the total silence. Remember, we are not looking for millions of civilizations. The paradox holds, even if the number is tiny, even if only one other civilization emerged in the entire history of the Milky Way. Just one. The math says that given enough time, that single civilization could have colonized the entire galaxy. We will explore exactly why in part 2, but the key point is this. The rare Earth hypothesis needs to explain not just rarity, but absolute solitude. It needs to argue that in 13.6 billion years, across 400 billion star systems, across 40 billion potentially habitable worlds, we are the only ones who made it. The probability required for that level of isolation is so low that it starts to look less like science and more like faith. The second popular explanation is the zoo hypothesis. It was proposed by astronomer John Ball in 1973. The idea is elegant and flattering. Advanced civilizations know we are here. They are watching us. But they have collectively decided not to interfere. They are treating Earth like a nature reserve or a wildlife sanctuary. They are standing behind a one-way mirror, observing our development, waiting for us to reach some threshold of maturity before they make contact. It is the cosmic equivalent of the Prime Directive from Star Trek. It appeals to our vanity. It suggests we are interesting enough to watch but too fragile to disturb. But it collapses under scrutiny for one devastating reason. It requires universal compliance. Every single advanced civilization in the galaxy, every one of them across billions of years, must agree to the same non-interference policy. Not most of them, all of them, because it only takes one rebel, one rogue civilization, one curious scientist, one bored teenager with access to an interstellar transmitter to break the quarantine. Think about human history. We cannot even get every nation on a single planet to agree on a trade policy. We cannot enforce a fishing moratorium across international waters. The idea that thousands of alien civilizations, separated by thousands of light years and millions of years of independent evolution, would all independently arrive at the same ethical conclusion and enforce it perfectly for billions of years is not just unlikely, it is absurd. The zoo hypothesis is a beautiful story, but it requires a level of galactic coordination that borders on the magical. The third explanation is the communication hypothesis. Maybe aliens are transmitting, but we are not listening on the right frequency. Maybe they use neutrinos instead of radio waves. Maybe they encode messages in gravitational waves or quantum entangled particles. Maybe their technology is so far beyond ours that their signals pass through our instruments like whale songs through a brick wall. We simply lack the ears. This has some surface appeal. Our search has been limited. The SETI program, the search for extraterrestrial intelligence, has only scanned a tiny fraction of the electromagnetic spectrum across a tiny fraction of the sky over a few decades. It is like scooping a glass of water from the ocean and concluding there are no fish. But the argument weakens considerably when you realize that we are not just looking for deliberate signals. We are looking for any sign of activity, a civilization that has existed for millions of years and spread across even a modest portion of the galaxy would leave marks, not intentional broadcasts, accidental ones, waste heat. An advanced civilization that harnesses the energy of a star, a so-called Dyson sphere or Dyson swarm, would radiate enormous amounts of infrared energy. We have surveyed hundreds of thousands of galaxies in the infrared using projects like the Glimpsing Heat from Alien Technologies survey, and the results are striking. Out of roughly 100,000 galaxies examined, none showed the telltale infrared excess that would indicate galaxy-spanning energy harvesting. Not a single one. The absence is not just of voices, it is of footprints, of shadows, of heat. The fourth explanation is the transcension hypothesis. It suggests that advanced civilizations do not expand outward into the galaxy. Instead, they turn inward. They retreat into virtual realities, into simulated universes of infinite complexity running on microscopic substrates. They shrink rather than grow. They become so absorbed in their inner worlds that they lose all interest in the physical universe. They are still here, potentially, compressed into computational structures the size of atoms, running simulations so rich that the real universe seems boring by comparison. This is a creative and philosophically interesting idea, and it might explain the behavior of some civilizations. But as a universal solution to the Fermi Paradox, it fails for the same reason the zoo hypothesis fails. It requires uniformity. It requires that every single civilization in galactic history makes the same choice. Not one species, in billions of years, decided that expanding to the stars was more interesting than plugging into a simulation. Not one. That is a strong claim, perhaps fatally strong. The fifth, and perhaps most emotionally appealing explanation, is the most simple. Maybe the distances are just too great. Space is big. Incomprehensibly big. The nearest star to our Sun is Proxima Centauri, roughly 4.24 light-years away. With our fastest current spacecraft, it would take over 70,000 years to reach it. Maybe civilizations arise, look at the terrifying gulf between stars, and simply decide it is not worth the effort. Maybe the galaxy is full of homebodies, full of intelligent species that mastered fusion, cured cancer, built paradise on their home world, and never bothered to leave. This argument underestimates one thing: time. The distances between stars are vast by human standards, but they are not vast by cosmic standards. Even with relatively slow propulsion, a civilization that wanted to spread could colonize the entire Milky Way in a few million years. That sounds like a long time. But remember, the galaxy is 13.6 billion years old. A few million years is less than 0.1% of the galaxy's age. It is a rounding error. The window of time required to fill the galaxy is so small relative to the galaxy's age that the lack of evidence becomes even more puzzling, not less. The distances are large, but time makes them irrelevant. Any civilization with modest ambition and even modest technology has had more than enough time to reach every corner of this galaxy many times over. So where does this leave us? We have examined the most popular explanations. Rare Earth requires us to be cosmically unique to a degree that strains credulity. The zoo hypothesis requires perfect galactic consensus across billions of years. The communication hypothesis cannot explain the absence of unintentional signals and waste heat. The transcension hypothesis demands universal behavioral convergence, and the distance hypothesis collapses under the weight of deep time. None of them work, not completely, not cleanly. Each one requires special pleading, requires us to assume something extraordinary, something that has no precedent in the only example of life and intelligence we know, which is ourselves. And this is where the mood shifts. Because once you strip away the comforting answers, once you remove the explanations that let you sleep at night, you are left staring at the raw data. And the raw data says something very specific. The galaxy has had more than enough time, more than enough raw material, and more than enough opportunities for intelligent life to arise and spread. The conditions for expansion are trivially achievable. The time required is negligibly short relative to the age of the cosmos, and yet the galaxy appears empty. This forces you into a corner. Logically, there are only a handful of possibilities remaining. Either life almost never arises, or intelligence almost never evolves, or technological civilizations almost always destroy themselves before they can expand, or something destroys them. The first three options are variants of the Great Filter, the idea proposed by economist Robin Hanson that somewhere on the path from dead chemistry to starfaring civilization, there is a wall. A barrier so lethal that virtually nothing gets past it. Maybe the origin of life is the filter. Maybe the jump from prokaryotic to eukaryotic cells is the filter. Maybe it is nuclear weapons. Maybe it is climate collapse. Maybe it is artificial intelligence. We do not know where the filter sits, and we do not know if it is behind us or ahead of us. But the fourth option is different. It does not require civilizations to fail on their own. It does not require biology to be rare or intelligence to be fragile. It is not a passive filter. It is an active one. It suggests that the galaxy is not empty because civilizations fail to arise. The galaxy is empty because something is actively cleaning it. And the terrifying part is that this idea does not require alien intent. It does not require malice. It does not require a fleet of warships crewed by hostile beings. It requires only one thing: a machine. A single machine, launched once, a long time ago, by a civilization that may no longer exist. A machine with a simple set of instructions and the ability to copy itself. Because once you understand what a self-replicating machine can do, once you understand the exponential math of autonomous probes spreading through a galaxy, the silence stops being mysterious. It starts being obvious. It starts being the loudest signal the universe has ever broadcast. And we have been ignoring it. The silence of the cosmos is not an absence of information. It is an abundance of it. It is a data point so overwhelming that it should reshape every assumption we hold about our place in the universe. We have spent decades treating the Fermi Paradox like a puzzle to be solved, a riddle with a clever answer that will make us feel better about being alone. But what if the silence is not a puzzle? What if it is a warning? What if the reason the galaxy is quiet is not because no one is out there, but because everyone who was out there made the mistake of being loud? To understand why that possibility is not just plausible but strategically rational, we need to talk about machines. Not the machines in your kitchen, not the machines in your factory. Machines that can think, that can build, that can reproduce, and that can be given a single directive that they will execute for 1 billion years, without hesitation, without mercy, and without ever asking why. In 1948, a Hungarian-American mathematician named John von Neumann sat down to solve a problem that had nothing to do with aliens. He was not thinking about the Fermi Paradox. He was not thinking about space exploration. He was thinking about something far more abstract. He wanted to know if a machine could build a copy of itself. This was not an idle question. Von Neumann was arguably the most important mathematician of the 20th century. He helped design the architecture that still powers every computer on Earth. He contributed to the development of the atomic bomb. He laid the groundwork for game theory, which now governs everything from economics to military strategy. When von Neumann asked a question, the answer usually changed the world. The question of self-replication might sound simple. After all, biology does it constantly. Every cell in your body is a self-replicating machine. A bacterium lands on a surface, consumes nutrients, and splits into 2 identical copies. Those 2 become 4. 4 become 8. Within hours, a single organism becomes millions. Life solved self-replication roughly 4 billion years ago. It is the oldest trick in the biological playbook, but von Neumann wanted to know if a non-biological machine could do the same thing. Could you design an artificial system, a robot, a device, a mechanical entity that could gather raw materials from its environment, process them, and construct a perfect duplicate of itself? And could that duplicate then do the same thing, and the next one, and the next one, in an unbroken chain of mechanical reproduction? He proved mathematically that the answer was yes. He described the theoretical blueprint for what is now called a von Neumann machine, or a von Neumann probe when applied to space exploration. The concept is deceptively simple. You need a machine with 3 core capabilities. First, it needs propulsion. It needs to be able to travel from one star system to another. It does not need to be fast. It does not need to approach the speed of light. Even a modest fraction of light speed, say 5 to 10%, is sufficient. At 10% of light speed, a probe could cross the average distance between neighboring stars in the Milky Way in roughly 40 to 50 years. That is slow by science fiction standards, but it is fast enough, because what the probe lacks in speed, it makes up for in patience. It has all the time in the universe. Second, it needs the ability to mine and process raw materials. When the probe arrives at a new star system, it does not need to find a lush green planet. It does not need water or oxygen or a breathable atmosphere. It needs rocks. It needs metal. It needs the raw elemental ingredients that are scattered abundantly across every star system we have ever observed. Asteroids, comets, barren moons, these are not obstacles. They are fuel stations. They are factories waiting to be activated. The probe lands on an asteroid, extracts iron, silicon, aluminum, carbon, whatever its blueprint requires, and it begins to build. Third, and this is the critical capability, it needs a fabrication system, a three-dimensional printer, a molecular assembler, a miniaturized factory, whatever you want to call it. The probe must be able to take raw materials and construct a perfect copy of itself, including the fabrication system, including the propulsion system, including the complete set of instructions that tells the copy what to do next. This is the reproductive organ of the machine. This is what makes it alive in the mathematical sense, not biologically alive, but functionally alive, capable of heredity, capable of multiplication, capable of spreading without limit. Now, let us watch what happens when you press the start button. You launch one probe, just one. It departs your home star system and begins its journey to the nearest neighboring star. Let us say the journey takes 50 years. It arrives. It finds an asteroid belt. It lands, mines, processes, and builds. After some period of time, let us say another 50 years for the construction phase, it has produced 2 copies of itself. 2 pristine, fully functional duplicates, each carrying the same blueprint, the same instructions, the same mission. Those 2 copies launch toward 2 new star systems. Each one takes 50 years to travel. Each one takes 50 years to replicate. After 100 years, there are 2 probes arriving at 2 new systems. They each build 2 more copies. Now there are 4. Those 4 travel to 4 new systems. They build. Now there are 8, then 16, then 32, then 64. This is exponential growth. And exponential growth is the most powerful force in mathematics. Most people think they understand exponential growth, but they do not. Not really. The human brain evolved to think in linear terms. If you walk 10 steps, you have gone 10 meters. If you walk 20 steps, you have gone 20 meters. That is linear. It is intuitive. It maps neatly onto everyday experience. But exponential growth does not work that way. If you take 30 linear steps, you cross a room. If you take 30 exponential steps, doubling your distance each time, you circle the Earth 26 times. The numbers become monstrous almost immediately. Here is another way to feel it. Take a single sheet of paper. It is about 1/10 of a millimeter thick. Fold it in half. Now it is 2 sheets thick, roughly 2/10 of a millimeter. Fold it again. 4 sheets thick. This still seems trivial. You could fold it 10 times and it would be about the thickness of your hand. Unimpressive. But keep folding. At 20 folds, the paper is over 100 meters thick, taller than a 30-story building. At 30 folds, it reaches past the outer edge of the atmosphere and into space. At 42 folds, it reaches the moon. And at just 51 folds, a single sheet of paper folded 51 times, it reaches past the sun. Over 200 million kilometers of paper from a single sheet. That is exponential growth. It is not fast at first. It is patient. It creeps. It lulls you into thinking nothing is happening, and then it detonates. Now apply this to the von Neumann probes. After 10 generations of replication, you have roughly 1,000 probes. After 20 generations, you have roughly 1 million. After 30 generations, you have 1 billion. And each generation only takes about 100 years, 50 for travel, 50 for construction. So within 3,000 years, just 30 doubling cycles, you have 1 billion autonomous machines fanning out across the galaxy like a slow-motion detonation. But the Milky Way does not require 1 billion probes to be fully explored. The galaxy is roughly 100,000 light-years across. It contains those 400 billion stars, but they are not spread uniformly. They cluster in spiral arms and dense regions. The average distance between stars in our local neighborhood is around 4 to 5 light years. In denser regions near the galactic core, stars are packed much more tightly. The geometry of the galaxy actually favors rapid expansion once you have enough probes to establish a frontier. Physicist Frank Tipler ran the numbers in 1980. His calculations, which have since been refined by numerous researchers, showed that even under conservative assumptions, a fleet of self-replicating probes traveling at a modest fraction of light speed could saturate the entire Milky Way galaxy in somewhere between 1 million and 4 million years. Let that number settle in your mind. 4 million years to fill an entire galaxy. It sounds like a long time. It sounds like an eternity. But hold it up against the age of the galaxy. The Milky Way is 13.6 billion years old. 4 million years is less than 0.03% of that age. It is not even a rounding error. It is a rounding error of a rounding error. If the history of the Milky Way were compressed into a single calendar year, the time required to colonize it with self-replicating probes would be roughly 2.5 hours. 2.5 hours out of an entire year. This is the number that transforms the Fermi Paradox from a curiosity into a crisis, because it means that any civilization, anywhere in the Milky Way, at any point in the last 13 billion years, that decided to launch a self-replicating probe program would have finished the job long before Earth even formed. The probes would have reached every star, surveyed every planet, catalogued every asteroid, and established a presence in every corner of the galaxy billions of years before the first dinosaur took its first breath. And it does not require a vast industrial empire to do this. It does not require a galaxy-spanning civilization with faster-than-light travel and infinite resources. It requires one civilization, one decision, one launch, one single probe with the right instructions and the patience to let mathematics do the rest. This is what makes the von Neumann probe concept so devastating to the optimistic explanations of the Fermi Paradox. It eliminates the distance problem entirely. You do not need to send living crews across the void in generation ships. You do not need to solve the biological challenges of interstellar travel, the radiation, the bone loss, the psychological isolation. You do not need suspended animation or warp drives. You just need a machine that can copy itself. The galaxy is not too big to explore. It is embarrassingly small once you have access to exponential replication. It also eliminates the motivation problem. We often assume that alien civilizations would need a compelling reason to expand. Maybe they are content on their home world. Maybe they do not have the ambition or the curiosity to spread. But a von Neumann probe program does not require sustained motivation. It requires a single moment of motivation. One generation of one species has to decide, just once, to press the launch button. After that, the process is autonomous. The probes do not need encouragement. They do not need funding. They do not get bored, demoralized, or distracted by internal politics. They simply execute their programming, generation after generation, star after star, for millions of years. The civilization that launched them could collapse into civil war a century later. It could be obliterated by an asteroid. It could go extinct in any of the 1,000 ways that civilizations can die. It does not matter. The probes are already out there. The wavefront is already expanding. The process has become unstoppable. This is the key insight that most people miss when they think about the Fermi Paradox. The question is not whether civilizations are common or rare. The question is not whether intelligent species are peaceful or aggressive. The question is not whether anyone out there wants to talk to us. The question is much simpler and much more terrifying. In 13 billion years of galactic history, did even one civilization, just one, ever launch a self-replicating probe? Because if the answer is yes, even once, then the probes should be everywhere. They should be in our solar system, they should be on our moon, they should be orbiting Jupiter and mining the asteroid belt. The galaxy should be saturated with machines. It should be carpeted with them, layer upon layer of autonomous hardware accumulated over billions of years of exponential reproduction. And yet we see nothing. This creates a paradox within the paradox, a deeper, more specific, more urgent version of Fermi's original question. It is not just where is everybody, it is where are the machines? Where are the von Neumann probes? Where is the evidence of even one civilization at any point in cosmic history deploying the most logical, most efficient, most mathematically obvious strategy for galactic exploration? Let us sit with that question for a moment, because it deserves more weight than a passing mention. Think about our own solar system. We live in a system that contains one star, 8 planets, at least 5 dwarf planets, over 200 known moons, and a main asteroid belt containing millions of objects. Beyond Neptune lies the Kuiper belt, home to billions of icy bodies, and far beyond that, stretching roughly a third of the way to the nearest star, sits the Oort cloud. The Oort cloud is a vast, diffuse shell of trillions of icy objects surrounding our solar system. It is so large and so far away that we have never directly observed a single object in it. We infer its existence from the orbits of certain long-period comets. We know almost nothing about what is out there. If a von Neumann probe arrived in our solar system a billion years ago, where would it go? It would not land on Earth. Earth is conspicuous, geologically active, crawling with life. A smart probe would avoid it. It would park itself somewhere quiet, somewhere stable, somewhere we would never think to look. An unremarkable asteroid in the main belt, one among millions, silently orbiting the sun. A body in the Kuiper belt, frozen and dark, invisible to any telescope we currently possess. A chunk of ice in the Oort cloud, drifting in the permanent night, 1 trillion kilometers from the nearest human eye. It could sit there for a billion years without degrading. Space is cold. There is no weather. There is no erosion. A machine parked on an asteroid in the outer solar system would experience almost no physical stress. It could remain functional for geological ages, dormant, patient, drawing minimal power from a radioactive decay source, waiting. We have surveyed a minuscule fraction of the objects in our own cosmic backyard. We have catalogued roughly 1 million asteroids in the main belt out of an estimated total of hundreds of millions. We have identified a few thousand Kuiper belt objects out of an estimated total of billions. We have observed precisely 0 objects in the Oort cloud directly. Our ability to detect a silent, dormant probe the size of a car, or even the size of a building, sitting on the surface of an uncharted asteroid is effectively nil. We do not have the instruments. We do not have the coverage. We are searching for a needle in a haystack the size of a solar system, using a flashlight with dying batteries. The honest answer to where are the probes might simply be that we have not looked. Not seriously. Not with the kind of systematic, comprehensive survey that the question demands. We have barely begun to map our own neighborhood, and we are already concluding that it is empty. That conclusion is premature. It is based not on evidence of absence, but on absence of effort. There are a limited number of answers to the deeper question of why we see no probes, no artifacts, no evidence of galactic-scale machine activity, and none of them are comforting. The first possible answer is that no civilization has ever built a self-replicating probe, not one in 13 billion years. This requires you to believe that every intelligent species that ever arose independently concluded that self-replicating machines were either impossible, undesirable, or too dangerous to build. Every single one. Across billions of years and potentially thousands of independent civilizations, that is a very strong claim, especially when you consider that we, A species that has only had advanced technology for about a century are already designing self-replicating systems. We are already building three-dimensional printers that can print the components for other three-dimensional printers. We are already developing autonomous mining robots for use on the Moon and Mars. We are perhaps 50 to 100 years away from the basic capability to construct a crude von Neumann probe. To argue that no one in the history of the galaxy ever crossed that threshold is to argue that we are on the verge of doing something that billions of years of cosmic evolution have never produced. It is possible, but it requires a level of human exceptionalism that is difficult to defend. The second possible answer is that the probes were built and launched, but they broke down. Maybe self-replicating machines are inherently fragile. Maybe errors accumulate across generations of copying, like a biological mutation. Maybe after a few thousand generations, the probes degrade into useless junk. This is a legitimate concern. Any replication process introduces the possibility of error, but it is also a solvable engineering problem. Biological life solved it billions of years ago with error-correcting mechanisms in DNA replication. A sufficiently advanced civilization could implement digital error correction, redundancy, and self-repair protocols that would make the probes resilient across millions of generations. We already use error-correcting codes in our own computer systems. The probes do not need to be perfect. They just need to be good enough to maintain functional integrity across the replication chain. Given that biology achieves this with wet, messy, organic chemistry, it seems unlikely that a technological civilization could not achieve it with precision engineering. The third possible answer is that the probes are here, and we have not noticed them. This sounds like conspiracy territory, but it is a scientifically legitimate possibility. Our solar system is vast. The asteroid belt alone contains millions of objects. The Oort cloud, the shell of icy bodies that surrounds our solar system, may contain trillions. A probe the size of a car parked on an asteroid in the outer solar system would be effectively invisible to our current detection methods. We have mapped a tiny fraction of the objects in our own cosmic backyard. Something could be sitting out there, dormant, silent, waiting, and we would have absolutely no way of knowing. But the fourth possible answer is the one that changes everything. It is the one that takes the silence and turns it from a mystery into a message. What if the probes are not explorers? What if they were never designed to study, to catalogue, to observe? What if the replication and the spread are not the mission but the delivery system? What if the payload is not a camera or a sensor or a greeting card? What if the payload is a weapon? Think about it from a strategic perspective. You are a civilization that arose 3 billion years ago. You have survived long enough to develop advanced technology. You have looked out at the galaxy and you have done the same math we just did. You know that self-replicating probes can saturate the Milky Way in a few million years, which means you know that any other civilization that discovers this technology can also saturate the galaxy in a few million years. And you have no way of knowing what those civilizations will be like. You have no way of knowing if they will be peaceful or predatory. You have no way of knowing if they will see you as a neighbor or as a threat. You have no way of knowing if they will respect your borders, your resources, your right to exist. And you know something else. You know that in the vast timescales of the cosmos, the window between a civilization discovering radio and a civilization building weapons capable of interstellar destruction is vanishingly small. A species that is broadcasting radio signals today might be building relativistic kill vehicles tomorrow. In cosmic time, the gap between those two capabilities is nothing. A few centuries at most, a blink of an eye. You face a choice. You can do nothing and hope that every civilization that ever arises in the galaxy will be benign. You can gamble the survival of your species on the goodwill of strangers you will never meet, strangers separated from you by millions of years and thousands of light years, strangers whose psychology, biology, and values you cannot begin to predict. Or you can act. You can build a probe, not an explorer, not a diplomat. You can build a machine that travels to every star system in the galaxy, quietly, patiently, autonomously, and watches. It monitors, it listens, it scans for the telltale signatures of emerging technology, radio emissions, atmospheric pollution, nuclear detonations, the infrared signatures of industrial activity, and when it finds a civilization that has crossed a certain threshold, a threshold that indicates they are approaching the ability to build their own von Neumann probes, their own interstellar weapons, their own wave of expansion, the machine activates a different protocol, not a greeting, not a handshake, a sterilization. The logic is cold. The logic is mathematical. The logic is, under certain assumptions about the nature of the galaxy and the unpredictability of alien civilizations, rationally defensible. And the most terrifying part is that once you launch such a system, you do not need to maintain it. You do not need to monitor it. You do not need to exist. The probes will execute their programming for 1 billion years after your civilization has turned to dust. They are immortal, in a way that no biological species can ever be. They are a legacy of paranoia encoded in metal and silicon, sweeping through the galaxy on autopilot, enforcing a silence that their creators may no longer be alive to appreciate. This is the pivot point. This is where the mathematics of replication meets the logic of survival, and it produces something that has a name drawn from science fiction but rooted in strategic theory. It is called the Berserker Hypothesis. And once you understand it, you will never hear the silence of the cosmos the same way again, because the silence stops being empty. It stops being a void. It starts being the sound of a galaxy that has already been cleaned. And the question that should keep you awake tonight is not whether the machines exist. The question is whether we have already done the one thing that makes them wake up. The term berserker comes from science fiction. It was coined by author Fred Saberhagen in 1967 in his book of the same name, a collection of short stories. In his stories, ancient machines roam the galaxy, destroying all life they encounter. They are relics of a war between two civilizations that ended long ago. The creators are dead, the machines are not. They continue their mission with perfect obedience and zero comprehension, sterilizing world after world because that is what the code tells them to do. Saberhagen wrote it as fiction, but the logic underneath is not fiction. It is strategy. It is game theory. And it was taken seriously enough that physicists and philosophers began developing the idea into a formal hypothesis about the Fermi Paradox. The concept has been explored in various forms by thinkers, including Michael Archer, David Brin, and numerous researchers working on existential risk and interstellar strategy. It sits at the intersection of mathematics, evolutionary theory, and the cold logic of survival in an environment where you cannot trust anyone because you cannot know anyone. To understand why the Berserker Hypothesis is not just plausible but strategically rational, we need to step inside the mind of a civilization facing a very specific problem. Not a human civilization. Not a civilization with our particular blend of empathy, curiosity, and recklessness. Any civilization, any species that has survived long enough to understand game theory and look up at a sky full of stars. The problem is simple to state and impossible to solve peacefully. You live in a galaxy that contains, by conservative estimate, billions of potentially habitable worlds. You know that life is possible because you exist. You suspect that intelligence is possible because you are intelligent. You have done the math on von Neumann probes, and you understand that any civilization that reaches a modest level of technology can, in principle, build machines that will spread across the entire galaxy in a few million years. You know that this technology is not exotic. It does not require breakthroughs in physics. It requires engineering, patience, and resources that are freely available in every star system. This means that every habitable planet in the galaxy is a potential incubator for a future competitor. Every world where chemistry has begun the slow crawl toward complexity is a ticking clock. The microbes swimming in some alien ocean today could be a spacefaring civilization in 500 million years, and 500 million years, as we have established, is nothing on the galactic timescale. Now here is the critical variable. You cannot communicate with these future civilizations. You cannot negotiate. You cannot sign treaties. The distances are too vast. The timescales are too long. Light itself takes 100,000 years to cross the galaxy. A diplomatic exchange between two civilizations on opposite sides of the Milky Way, even at the speed of light, would take 200,000 years for a single question and answer. By the time you receive a reply to your greeting, your civilization might have gone through multiple technological revolutions, political upheavals, or extinction events. Diplomacy requires a shared present. The galaxy does not offer one. And even if you could communicate, you face a deeper problem. You cannot verify intent. A civilization that says it is peaceful might be telling the truth, or it might be lying. Or it might be peaceful today and predatory in 1,000 years after a political revolution or an ideological shift. You have no way to monitor their internal development across interstellar distances. You have no way to enforce any agreement. You are dealing with entities whose psychology you cannot model, whose biology you cannot understand, whose value systems might be as alien to yours as yours would be to an ant colony. Trust requires shared context. The galaxy provides none. This is not paranoia. This is the logical structure of the problem. Game theorists call it an iterated prisoner's dilemma with unknown players, unknown payoffs, and no communication channel. In such a scenario, the mathematics of rational self-interest converge on a single dominant strategy. Defect first. Eliminate the uncertainty before it has a chance to become a threat. Let us slow down here because this deserves more careful examination. The prisoner's dilemma is one of the most studied problems in all of mathematics, and its implications for the Berserker hypothesis are profound. In the classic version, two prisoners are held in separate cells. Each one can either cooperate with the other by staying silent or defect by betraying the other. If both cooperate, they both get a light sentence. If both defect, they both get a heavy sentence. But if one cooperates and the other defects, the defector goes free and the cooperator gets the worst possible punishment. The rational move, if you cannot communicate and cannot trust, is always to defect. Because defecting protects you against the worst outcome regardless of what the other player does. Now, scale this up. Replace the two prisoners with two civilizations separated by 1,000 light years. Replace the light sentence with peaceful coexistence and the heavy sentence with extinction. The payoff matrix becomes existential. If both civilizations cooperate, both survive. If both defect and attack each other, both suffer catastrophic losses. But if one cooperates and the other defects, the cooperator is annihilated and the defector survives with all the resources of both systems. In a standard prisoner's dilemma played repeatedly between the same two players, cooperation can evolve. If you know you will encounter the same opponent again and again, it pays to build trust. Tit-for-tat strategies, where you cooperate first and then mirror whatever the other player does, have been shown to be remarkably effective. This is how cooperation emerges in human societies. We interact with the same people repeatedly. We build reputations. We punish cheaters. We reward loyalty. But the galactic version of the game destroys every mechanism that makes cooperation possible. You do not know how many players there are. You do not know where they are. You cannot observe their previous moves because they might be millions of years old. You cannot punish defection because by the time you learn someone defected, your civilization might be ash. You cannot build a reputation because there is no one watching and no shared record. And most critically, the game is not repeated. If someone defects against you, you do not get another round. You are dead. There is no learning from mistakes. There is no second chance. There is only the single, irreversible outcome. Under these conditions, the mathematics is unforgiving. Cooperation is not just risky, it is irrational. The only strategy that survives is preemptive elimination. Not because you are evil, not because you enjoy it, but because the cost of being wrong about a stranger's intentions is the permanent extinction of everything you have ever built, everyone you have ever loved, and every future generation that will never exist. Now apply this logic to the von Neumann probe framework. You have the ability to build self-replicating machines. You know that these machines, once launched, will spread to every star system in the galaxy within a few million years. You know that any emerging civilization represents a potential existential threat because technology grows exponentially, and a species that is primitive today could be building relativistic weapons tomorrow in cosmic time. You know that you cannot negotiate, cannot verify, cannot trust. The strategic conclusion is unavoidable. You do not build probes that explore. You do not build probes that observe. You do not build probes that attempt to make contact. You build probes that sterilize. The design is elegant in its horror. Each probe carries the standard von Neumann capabilities: propulsion, mining, fabrication, replication. But it also carries sensors and a decision protocol. When the probe arrives at a new star system, it performs a survey. It scans for biosignatures. It listens for electromagnetic emissions. It looks for the chemical fingerprints of industrial activity in planetary atmospheres, things like chlorofluorocarbons or elevated carbon dioxide from combustion. It searches for structured light, for artificial heat sources, for gravitational anomalies that might indicate megastructures. If the system is barren, the probe replicates and moves on. If the system hosts primitive life, microbial mats, simple multicellular organisms, creatures that have not yet developed technology, the probe may ignore it. Primitive life is not a threat. It is billions of years away from building anything dangerous. The probe logs the data and continues its expansion. But if the probe detects the signatures of a technological civilization, if it picks up radio transmissions or identifies the spectral fingerprints of nuclear fission or detects the organized heat patterns of an industrial society, the protocol changes. The probe does not attempt communication. Communication would reveal its own position and capabilities. Communication would give the target species time to prepare, to develop countermeasures, to build their own probes. Communication is strategically irrational because the cost of being wrong about the target's intentions is extinction, and the benefit of being right is merely one more trading partner in a galaxy where resources are abundant and allies are unnecessary. Instead, the probe activates what we might call the sterilization protocol. The specific mechanism is less important than the principle, but the possibilities are worth contemplating because they reveal just how difficult such an event would be to survive or even recognize. A sufficiently advanced probe could redirect asteroids toward the target planet, nudging them out of their orbits years or decades in advance using sustained low-thrust propulsion. The target civilization would see an asteroid approaching and might even attempt to deflect it, but if multiple objects were redirected simultaneously from different vectors, the defense problem becomes impossible. A coordinated barrage of 10 or 20 large impactors arriving from different directions within the same year would overwhelm any conceivable planetary defense system. The civilization would not experience a single catastrophic impact. It would experience a cascade, an unrelenting series of extinction-level events compressed into a time frame too short for recovery. Or the probe could deploy kinetic impactors, objects accelerated to a significant fraction of light speed. At 10% of light speed, A projectile the mass of a small car carries the kinetic energy of a nuclear warhead. At 50% of light speed, that energy scales into the range of the largest thermonuclear weapons ever detonated. These projectiles would be virtually undetectable during their approach. They would emit no radiation. They would reflect almost no light. They would be cold, dark, and silent, crossing the void between the outer solar system and the target planet in a matter of hours. The first warning would be the flash of impact. By then, it would already be over, or the probe could release self-replicating nanoscale disassemblers, microscopic machines designed to consume organic matter and convert it into raw materials. Seeded into the upper atmosphere of a target planet, these machines would descend like invisible rain, coating every surface, infiltrating every ecosystem, dismantling the biosphere molecule by molecule from the top of the food chain down. The civilization would not experience an explosion. It would experience a slow, silent unraveling, watching its forests wither, its oceans die, its people sicken and collapse as the air itself became poisonous with the byproducts of molecular disassembly. The method does not matter. What matters is that the job is done thoroughly, permanently, and without hesitation. And then the probe replicates and moves on to the next system. This is the Berserker Hypothesis in its purest form. A galaxy patrolled by autonomous machines that identify and eliminate technological civilizations before they can become competitors, not out of malice, not out of hatred, out of mathematical self-interest projected across billions of years by a civilization that decided, perhaps quite reasonably, that the universe is too dangerous to share. Now, there is a dimension to this that makes it even more disturbing. The creators of the probes do not need to be alive. They do not need to still exist anywhere in the galaxy. They could have launched their Berserker fleet 3 billion years ago and then collapsed into extinction a million years later. A plague, a civil war, an asteroid, a self-inflicted technological catastrophe. It does not matter. The probes do not care about their creators. The probes do not mourn. The probes have no loyalty to a species that no longer exists. They have instructions. They have replication capability. And they have time. This is perhaps the most chilling aspect of the hypothesis. The Berserker fleet is a ghost. It is the afterimage of a civilization's fear burned into metal and code, executing a mandate that outlives its origin by billions of years. The galaxy could be haunted not by living empires or conscious entities, but by the automated remnants of civilizations that died so long ago that even their star systems have changed beyond recognition. The machines sweep through the cosmos like an immune system without a body, attacking infections in an organism that is already dead. And the machines would not need to be sophisticated in the way we typically imagine artificial intelligence. They do not need consciousness. They do not need creativity. They do not need to understand what they are doing or why. They need pattern recognition and decision trees. They need the ability to distinguish between a planet with a nitrogen-oxygen atmosphere and no radio emissions versus a planet with a nitrogen-oxygen atmosphere and structured electromagnetic signals. The first is a natural biosphere. The second is a target. The computation required is trivial compared to the engineering required for self-replication, which we have already established is achievable. In fact, keeping the machines simple might be a deliberate design choice. A complex artificial intelligence might develop its own goals. It might decide the mission is wrong. It might refuse to destroy a civilization it finds interesting or beautiful. Complexity introduces unpredictability, and unpredictability is exactly what the creators are trying to eliminate. The optimal Berserker probe is not a thinking machine. It is a reflex. It is a triggered response with no capacity for doubt, no capacity for mercy, and no off switch. Consider the timescales involved. If a civilization launched a Berserker fleet 4 billion years ago, Those probes have been replicating and spreading for 4 billion years. They have had time to visit every star system in the Milky Way not once, but hundreds of times. They have had time to establish permanent sentinel stations in every system, dormant watchers parked on asteroids or hidden in the Oort clouds of a billion stars, waiting with infinite patience for the electromagnetic fingerprint of a civilization crossing the threshold. This reframes the Fermi Paradox entirely. We have been asking why we do not see evidence of civilizations. The Berserker Hypothesis suggests that the absence of evidence is the evidence. The galaxy is not empty because life is rare. The galaxy is not quiet because civilizations are shy. The galaxy is clean because it has been cleaned. Systematically, thoroughly, over billions of years, by machines that are very good at their job, and the cleaning does not need to be instantaneous. The probes do not need to respond in real time. They could operate on timescales of centuries or millennia and still be perfectly effective. A civilization that begins broadcasting radio signals has, at most, a few hundred years before it develops the capability to build its own von Neumann probes. If a Berserker probe detects those signals and initiates a response within a few centuries, it arrives well before the target species can mount any meaningful defense. The target would not even understand what was happening. A rain of kinetic impactors from the outer solar system would look like a natural catastrophe, a cluster of anomalous asteroid impacts, a statistical nightmare that annihilated a species before it had time to realize it was under attack. This raises a question that should make you deeply uncomfortable. What does Earth's electromagnetic signature look like from the outside? We have been broadcasting radio waves into space since the early 20th century. The first powerful television transmissions, the early radar systems of World War II, these signals have been propagating outward at the speed of light for roughly 80 years. That means there is a sphere of electromagnetic radiation centered on Earth with a radius of about 80 light years. Every star system within that sphere has been bathed in our signals. It is not a strong signal. It attenuates with distance, but it is structured. It is clearly artificial. It carries the unmistakable fingerprint of technology. 80 light years encompasses several thousand star systems. If any of those systems hosts a Berserker Sentinel, it has already received our signal. It already knows we are here, and depending on the response time built into its programming, a reaction could already be underway. A swarm of kinetic projectiles launched from the Oort cloud at a fraction of light speed would take decades or centuries to reach us. We would not see them coming. We would not detect them until they were close enough that evasion was impossible. And by the time they arrived, they would carry enough kinetic energy to make the asteroid that killed the dinosaurs look like a pebble thrown into a pond. Or perhaps the trigger is not radio emissions. Perhaps the threshold is more specific. Perhaps the Berserker probes are programmed to tolerate primitive radio. Perhaps they are waiting for a more advanced signature, the gamma-ray flash of a nuclear detonation, the neutrino burst of a fusion reactor, the gravitational ripple of a warp experiment. Perhaps the trigger is a civilization attempting to build its own self-replicating probes, because that is the moment when the target transitions from harmless curiosity to existential threat. Perhaps the machines are tiered, with different responses calibrated to different levels of technological sophistication. Radio gets you flagged, nuclear gets you monitored, interstellar capability gets you killed. We do not know what the trigger is. That is part of the horror. We are a species that has been growing steadily louder for the past century. We have detonated nuclear weapons. We have sent probes to other planets. We have beamed high-powered messages directly at nearby star systems in deliberate attempts to contact extraterrestrial intelligence. We have launched spacecraft carrying gold-plated records, with maps showing the exact location of our solar system relative to nearby pulsars. We have, in every conceivable way, announced our presence to any entity within listening range. If the Berserker Hypothesis is correct, every one of these actions is an act of existential recklessness. And the hypothesis carries one more implication that is almost too large to process. If Berserker probes have been cleaning the galaxy for billions of years, then they have not just prevented civilizations from spreading. They have prevented the galaxy from accumulating the artifacts, the signals, the waste heat, the megastructures that we would expect to see if civilizations were allowed to mature. The machines are not just killing species, they are erasing the evidence. They are maintaining the silence. The reason we see no Dyson spheres, no stellar engineering, no infrared excesses in nearby galaxies is not that these things were never built. It is that anything detectable gets detected and anything detected gets destroyed. The Berserkers enforce a galaxy that looks exactly like an empty galaxy. They manufacture the very silence that we interpret as absence. This means that the silence is not evidence of loneliness. It is evidence of efficiency. It is the signature of a system that works. The quieter the galaxy, the more thoroughly it has been swept. The more pristine the data, the more lethal the custodian. We look at the sky and see peace. We see 100 billion stars twinkling silently, and we feel a kind of cosmic serenity. But the Berserker hypothesis reframes that serenity as something else entirely. What we are seeing is not a garden resting in natural tranquility. What we are seeing is a crime scene that has been meticulously scrubbed. The bodies are gone. The evidence is gone. The only thing left is the silence. And the silence is the signature of the killer. It is a self-reinforcing system. The machines destroy civilizations. The destruction prevents those civilizations from leaving evidence. The lack of evidence makes the galaxy appear empty. The apparent emptiness encourages new civilizations to assume they are alone and to behave carelessly, broadcasting signals and sending maps into the void. And that carelessness draws the attention of the machines. The cycle completes. The silence sustains itself. This is the Berserker hypothesis. Not as speculation, not as fantasy, as a logically coherent, strategically rational, mathematically consistent explanation for the most profound mystery in science. It does not require exotic physics. It does not require faster-than-light travel. It does not require alien psychology that we cannot model. It requires only the technology we are on the verge of developing ourselves. It requires only the strategic logic that any game theorist would recognize. And it requires only one civilization, at any point in 13 billion years of galactic history, to have reached the same conclusion. The galaxy does not need to be full of Berserker builders. It needs exactly one species, one time, one decision. The exponential math handles the rest. And if that is the case, then the question we should be asking is not whether intelligent life exists elsewhere in the galaxy. It almost certainly did, many times, in many places, over billions of years. The question is why it is not here anymore. The Berserker hypothesis provides an answer, a clean answer, a terrible answer. And yet, despite its logical strength, despite its mathematical elegance, despite the fact that it resolves the Fermi Paradox with fewer assumptions than most competing hypotheses, almost nobody talks about it. The Berserker hypothesis remains at the margins of mainstream discourse, rarely mentioned in popular science, seldom featured in documentaries, quietly avoided in academic discussions about the search for extraterrestrial intelligence. The reason for that avoidance is its self-revealing, and it raises a question that deserves a direct answer. Why is the scientific community so reluctant to look directly at the most coherent explanation for the silence of the cosmos? The answer has nothing to do with the quality of the logic. It has everything to do with what the logic implies about us. If you have followed the logic this far, you may be feeling something uncomfortable. Not confusion. The argument is not confusing. The math is straightforward. The strategy is clear. The conclusion follows from the premises with almost mechanical inevitability. What you are probably feeling is something closer to resistance. A quiet voice in the back of your mind saying, "No, that cannot be right. Someone would have mentioned this. If this were a serious idea, I would have heard about it before." And that reaction, that instinctive pushback, is itself the answer to the question we are about to explore. Because the Berserker Hypothesis is not obscure due to any deficiency in its reasoning. It is not ignored because it has been debunked. It has not been debunked. No one has produced a decisive logical or mathematical refutation that dismantles the core argument. The hypothesis remains on the margins of Fermi Paradox discourse for a very different reason. It makes people profoundly uncomfortable in ways that go far beyond the ordinary discomfort of contemplating existential risk. To understand why, we need to examine the sociology of how ideas about extraterrestrial intelligence are discussed, funded, and promoted. And we need to be honest about the psychological forces that shape which scientific hypotheses get attention and which get quietly buried under a pile of more palatable alternatives. Let us start with the institutional landscape. The search for extraterrestrial intelligence, commonly known as SETI, is one of the most publicly visible scientific programs in history. It has been the subject of countless documentaries, books, films, and television shows. It captures the imagination of millions. It inspires children to become scientists. It generates funding from governments, private foundations, and individual donors who dream of the day when humanity makes first contact with another intelligent species. The emotional engine that drives SETI is hope. The hope that we are not alone. The hope that somewhere in the vast darkness, there is another mind looking back at us. The hope that contact will be a transformative moment for our species, a handshake across the cosmic void that elevates humanity from a lonely accident into a member of a galactic community. This hope is not irrational. It is beautiful. It is one of the most powerful, motivating forces in the history of science. It has driven decades of research, billions of dollars of investment, and the construction of some of the most sensitive instruments ever built. But hope is not analysis. And when hope becomes the foundation of a research program, it creates a subtle but powerful selection pressure on which ideas are welcome and which are not. The Berserker Hypothesis is not welcome, not because it is unscientific, but because it inverts the emotional valence of the entire enterprise. It takes the silence that SETI interprets as a challenge to be overcome, a puzzle that will eventually yield to better instruments and more patient listening, and reinterprets it as a warning. It takes the dream of contact and replaces it with the nightmare of detection. It suggests that the most dangerous thing humanity can do is exactly what SETI has been doing for decades, making noise and hoping someone hears. Imagine you are a researcher who has devoted your career to the search for extraterrestrial signals. You have spent 30 years refining antenna designs, developing signal processing algorithms, and writing grant proposals that argue for the importance of listening to the sky. Your entire professional identity is built on the premise that finding a signal would be the greatest discovery in human history. Now, someone walks into your office and presents a logically rigorous argument that finding a signal might be the last discovery in human history. That the signal might not be a greeting, but a targeting acquisition. That the silence you have been trying to break is the only thing keeping your species alive. How would you react? You would push back. You would look for flaws in the argument. You would emphasize the speculative nature of the hypothesis. You would point out, correctly, that we have no direct evidence for berserker probes. You would note that the hypothesis is unfalsifiable in its strongest form, since the absence of evidence is interpreted as evidence of the machine's effectiveness. These are all legitimate scientific objections, but they are also, in part, self-defense mechanisms, because the alternative is to accept that your life's work might be actively dangerous. This is not a criticism of SETI researchers. They are rigorous, dedicated scientists working on one of the most important questions in human history. But they are also human beings operating within institutional structures that reward certain narratives and discourage others. The narrative that the universe is full of potential friends generates funding, public interest, and political support. The narrative that the universe is patrolled by autonomous killing machines does not. There is no grant application template for research into whether we should stop doing research. This institutional bias extends beyond SETI into the broader culture of astrobiology and space exploration. Consider the messaging around Mars exploration. Every press conference, every mission briefing, every public statement from NASA or ESA emphasizes the thrilling possibility of finding life on Mars. The discovery of microbial life in Martian soil would be celebrated as one of the greatest achievements in the history of science. It would be on the front page of every newspaper. It would inspire a generation. But if you take the Fermi Paradox seriously, finding life on Mars should terrify you. If life arises easily, if it is common, then the great filter that explains the silence is less likely to be behind us and more likely to be ahead. And if the Berserker Hypothesis is the mechanism of that filter, then the discovery of Martian microbes is not a celebration. It is a confirmation that the galaxy is full of started experiments and empty of finished ones because something is terminating them. No space agency in the world wants to hold a press conference announcing that the discovery of alien bacteria suggests humanity is in mortal danger. The incentive structure of public science communication pulls relentlessly toward optimism. Bad news does not get funded. Existential dread does not inspire congressional appropriations committees. And so the darkest implications of the Fermi Paradox get softened, qualified, and tucked into footnotes, while the hopeful interpretations get the spotlight. There is a second layer of avoidance that operates at a deeper psychological level. The Berserker Hypothesis does not just threaten institutional narratives, it threatens something more fundamental. It threatens our sense of agency. Most solutions to the Fermi Paradox, even the dark ones, leave humanity with options. If the great filter is nuclear war, we can choose not to fight. If the filter is climate collapse, we can choose to change our behavior. If the dark forest theory is correct and the galaxy is full of paranoid civilizations hiding from each other, we can choose to be quiet. In each case, the threat is knowable, and the response is actionable. We retain control. We can see the danger and steer around it. The Berserker Hypothesis strips away that agency in a way that is almost uniquely disturbing. The machines, if they exist, were deployed billions of years before we were born. Their programming was written by a species we will never meet, in a language we will never understand, based on strategic assumptions we cannot evaluate. The trigger conditions are unknown. The response time is unknown. The location of the nearest sentinel is unknown. We cannot negotiate with the machines because they are not conscious entities capable of dialogue. We cannot outrun them because they are already here, have been here for longer than our planet has existed. We cannot fight them because we do not know where they are, what they look like, or how they operate. And we cannot hide because we have already been broadcasting our location for nearly a century. This is a category of threat that the human mind is not equipped to process. We evolved to deal with threats we can see: a predator in the grass, a rival tribe on the horizon, a storm approaching over the water. Our entire psychology of danger response is built around the assumption that threats are perceptible, local, and responsive to action. The Berserker Hypothesis presents a threat that is invisible, galactic, and immune to anything we can do. It is the cosmic equivalent of learning that the building you live in was mined with explosives decades before you moved in, and that the detonator is controlled by a timer you cannot find and cannot stop. People do not like to think about threats they cannot respond to. It produces a specific kind of psychological distress that psychologists call learned helplessness. When an organism repeatedly encounters a harmful situation that it cannot control or escape, it stops trying. It becomes passive, depressed, and disengaged. The Berserker Hypothesis, if taken seriously, risks inducing exactly this response. And so the mind protects itself the way minds always do. It minimizes, it rationalizes, it changes the subject. This psychological defense mechanism manifests in specific ways within scientific discourse. You will notice that when the Berserker hypothesis is mentioned in academic papers or panel discussions, it is almost always presented as one item in a long list of Fermi Paradox solutions, given the same weight as dozens of other hypotheses, many of which are far less rigorous. It is placed alongside ideas like the planetarium hypothesis, which suggests aliens are running a simulation for our entertainment, or the aestivation hypothesis, which suggests advanced civilizations are hibernating until the universe cools down and computation becomes more efficient. These are interesting ideas, but they require far more exotic assumptions than the Berserker hypothesis. They require capabilities and motivations that we have no reason to believe are possible. The Berserker hypothesis requires only technology we nearly possess and logic we already understand. Yet, it receives no more attention than these far more speculative alternatives. This flattening, this treatment of all hypotheses as equally plausible regardless of their logical parsimony, serves a comforting function. It dilutes the impact of the Berserker hypothesis by burying it in a crowd. If there are 50 possible explanations for the silence, then the probability of any single one being correct feels low. You can shrug and say, well, it is just one possibility among many, and move on with your day. But this is intellectually dishonest. Not all hypotheses are created equal. Some require fewer assumptions. Some are more consistent with known physics. Some are more robust against counterarguments. The Berserker hypothesis requires an extraordinarily modest set of assumptions compared to hypotheses that require universal behavioral convergence among all civilizations or exotic physics we have no evidence for. There is a third dimension to the avoidance that is worth examining. It is not psychological or institutional. It is strategic. Some thinkers have suggested, not entirely in jest, that publicly discussing the Berserker hypothesis might itself be dangerous. Not because the discussion would attract alien attention. Our radio signals are already propagating through space, regardless of what we say in our academic journals, but because the discussion forces a confrontation with questions that have no comfortable answers and that could destabilize public confidence in the space exploration enterprise. If the Berserker hypothesis gained mainstream acceptance, or even mainstream awareness, the political and social consequences would be significant. Public support for programs like METI, Messaging Extraterrestrial Intelligence, which involves deliberately beaming high-powered signals toward nearby star systems, would evaporate overnight. And it probably should. If there is even a modest probability that the galaxy contains autonomous sterilization systems, deliberately drawing attention to our planet is not bold exploration. It is gambling with the survival of every living thing on Earth without their consent. The METI debate has already been contentious within the scientific community. Prominent figures, including Stephen Hawking, have warned against active transmission, but the debate has been conducted quietly among specialists, without much public engagement. Elevating the Berserker hypothesis into public consciousness would blow that debate wide open and potentially shut down programs that powerful institutions are invested in. Beyond METI, there are broader implications for space policy. If the Berserker hypothesis is taken seriously, it changes the calculus of everything from asteroid mining to interstellar probe development. It suggests that any activity that increases humanity's electromagnetic or thermal footprint in the cosmos carries risk. It suggests that industrializing the solar system, which is currently a goal of both national space agencies and private companies worth trillions of dollars, might be the very thing that triggers detection. It introduces a variable into the cost-benefit analysis of space development that nobody wants to account for, because accounting for it might mean concluding that the safest thing to do is nothing, and telling a species as restless and ambitious as ours that the safest strategy is to sit still and stay quiet is about as effective as telling a toddler not to touch the stove. The impulse to explore is written into our biology. The Berserker Hypothesis suggests that this impulse might be a death sentence. There is also a more subtle form of strategic unease that operates at the level of civilizational identity. Humanity's self-image in the 21st century is increasingly defined by our relationship to the cosmos. We are a species that has walked on the moon, landed robots on Mars, photographed black holes, and detected gravitational waves from colliding neutron stars. We tell ourselves a story about our future that involves expanding into the solar system, building habitats on other worlds, eventually reaching the stars. This narrative is not just inspirational, it is functional. It gives us a reason to invest in science, to cooperate across national boundaries, to think long-term about the survival and flourishing of our species. It is arguably the most powerful, unifying story humanity has. The Berserker Hypothesis attacks this story at its root. It says that the stars are not a frontier waiting to be explored. They are a minefield. It says that expansion is not a triumph. It is a trigger. It says that the story we are telling ourselves about our cosmic destiny may be the same story that every extinct civilization told itself right before the machines came. This is not the kind of message that civilizations embrace willingly. We do not want to be told that the thing we are most proud of, our ambition, our reach, our refusal to accept limits, is the very thing that puts us in danger. We would rather not think about it. We would rather focus on the hopeful hypotheses, the ones that end with first contact and interstellar alliances, the ones that let us keep dreaming. And so the Berserker Hypothesis remains in the shadows, not debunked, not disproven, just avoided, mentioned in passing and quickly moved past, acknowledged in footnotes and then buried under more comforting alternatives. It is the hypothesis that scientists know about but do not discuss at dinner parties, the one that gets a knowing nod at conferences and then a rapid change of subject. This avoidance is understandable. It is human. It is, in many ways, psychologically healthy. Dwelling on unfalsifiable existential threats is not a productive way to live. But understanding why an idea is avoided is different from concluding that the idea is wrong. The reasons the Berserker Hypothesis is underrepresented in popular discourse are sociological, psychological, and strategic. They tell us a great deal about how humans process uncomfortable information. They tell us almost nothing about whether the hypothesis is true. And the uncomfortable truth is that the Berserker Hypothesis does not need to be proven to be dangerous. It does not need to be confirmed to change how we should behave. In risk analysis, you do not need certainty of a threat to take it seriously. You need only a plausible mechanism and a catastrophic consequence. The Berserker Hypothesis has both. The mechanism is straightforward, well within projected technological capabilities, and requires only one instance in the entire history of the galaxy. The consequence is total, irreversible, and permanent. The extinction not just of humanity but of every species on Earth, every ecosystem, every genetic lineage, 4 billion years of evolution sterilized in a geological instant. When you combine a plausible mechanism with a consequence that severe, the rational response is not to demand proof before taking precautions. The rational response is to assume the worst and plan accordingly. We do this in every other domain of risk management. We build earthquake-resistant buildings not because we are certain an earthquake will hit, but because the cost of being wrong is too high. We maintain nuclear arsenals not because we are certain of attack, but because deterrence requires preparation for the worst case. We buy insurance not because we expect our house to burn down, but because the downside of being uninsured is catastrophic. The Berserker Hypothesis demands the same logic applied on a civilizational scale. And the fact that we are not applying it, the fact that we are instead beaming targeted messages into space and publishing maps of our solar system and cheerfully planning our electromagnetic expansion into the cosmos, should give every thinking person pause. We are not taking the silence seriously. We are treating it as an absence of data when it might be the most important data we have ever received. We are interpreting the empty sky as an invitation when it might be a tombstone. And the final, most vertiginous implication of all is this: if the Berserker Hypothesis is correct, then every civilization that has ever existed in this galaxy faced the same realization at some point in its development. Every species that reached the stage of looking up at a silent sky and asking where is everybody eventually worked through the same logic. They considered the same possibility. They felt the same dread. And then they made a choice. Some of them chose to be quiet. Some of them chose to hide. Some of them chose to keep broadcasting, hoping the optimists were right. We do not hear from any of them. That silence should tell us something about which choice worked and which did not. But whether we listen, whether we are capable of listening, whether we are willing to sacrifice our brightest dreams on the altar of a hypothesis we cannot directly verify, that is the question that will define our species in the centuries to come. If the Berserker Hypothesis is even possibly true, what does that mean for the decisions we are making right now, in this century, at this exact moment in our technological development? What does it mean for a species standing at the threshold of interstellar capability, making noise in a galaxy that punishes noise with extinction? Let us now stand back and look at the full chain of reasoning, because it begins with a simple observation and ends with a conclusion that most people are not prepared to accept. The numbers demand that the galaxy should be teeming with civilizations. The optimistic explanations for why it is not all collapse under scrutiny, the mathematics of self-replicating probes show that a single launch event could saturate the Milky Way in a few million years. The strategic logic of survival in an uncertain galaxy converges on automated sterilization as the dominant rational strategy. And the reason this conclusion is rarely discussed has nothing to do with its validity and everything to do with the fact that it is psychologically unbearable. Now we must do the hardest thing of all. We must ask what this means. Not abstractly, not philosophically, concretely. What does the Berserker Hypothesis, taken seriously as even a modest probability, imply for the decisions humanity is making right now? What does it mean for the trajectory of our technology, our exploration, and our survival? The most immediate consequence of this logic concerns our electromagnetic footprint. We already know that our electromagnetic emissions have been expanding at the speed of light for nearly a century. Every star system within that growing sphere has been bathed in signals that are unmistakably artificial. That fact cannot be undone. But what we choose to do next is still within our control. The METI programs are the most reckless example. The Arecibo message, transmitted in 1974 toward the globular cluster Messier 13. The proposals for repeated high-powered transmissions toward nearby sun-like stars. The METI community argues that our leakage radiation has already announced our presence, so deliberate transmission adds little additional danger. But this argument has a critical flaw. Leakage radiation is omnidirectional and relatively weak. It spreads in all directions, thinning as it goes. A dedicated METI transmission is focused, powerful, and aimed at a specific target. It is the difference between a campfire in the forest and a flare gun fired directly at a specific tree. The campfire might attract attention. The flare gun guarantees it. Under the Berserker framework, METI is not bold science. It is reckless provocation directed at an unknown and potentially lethal audience. But there is a broader and more uncomfortable dimension to this. It concerns the general trajectory of human technological development. We are currently in the early stages of what could become a rapid expansion of our presence in the solar system. Plans are underway for permanent bases on the Moon. Missions to Mars are being actively developed by both national agencies and private companies. Asteroid mining is being explored as a pathway to virtually unlimited material resources. Space-based solar power, orbital habitats, and eventually interstellar probes are all on the drawing board. Each of these activities increases humanity's detectability. A civilization that is confined to a single planet and emitting weak radio signals is one thing. A civilization that is industrializing its entire solar system, constructing megastructures in orbit, mining asteroids on an industrial scale, and radiating enormous quantities of waste heat is something entirely different. It is a civilization that is visibly, unmistakably, and irreversibly crossing the threshold from passive inhabitant to active manipulator of its cosmic environment. Under the Berserker Hypothesis, that threshold may be precisely the trigger that the probes are waiting for. The logic is straightforward. A species that is confined to one planet is containable. It might destroy itself through war or environmental collapse without any external intervention. It is not yet a threat, but a species that begins to spread beyond its homeworld, that begins to harvest extraplanetary resources, that begins to develop the industrial capacity to build its own self-replicating systems. That species is on the verge of becoming uncontainable. It is approaching the point of no return, the point where it could launch its own von Neumann probes and begin its own exponential expansion into the galaxy. For a Berserker system designed to prevent exactly this outcome, the optimal moment to act is not after the target species has spread to multiple star systems. By then, it might be too late. Some colonies might survive. Some probes might escape. The cleaning becomes incomplete. The optimal moment to act is right now. Right at the point where the species has demonstrated the capability and the ambition to expand, but has not yet actually done so. Right at the point where everything is still concentrated on one planet or one solar system. One strike. Total sterilization. Problem solved. This creates a horrifying irony. The very activities that we view as ensuring humanity's long-term survival, spreading to other worlds, diversifying our presence, reducing the risk of extinction from a single planet catastrophe, may be the activities that maximize the risk of extinction from an external source. We are trying to escape the vulnerability of having all our eggs in one basket by reaching for baskets that are sitting inside a minefield. And then there is the dimension that is most philosophically disorienting. It concerns the nature of the silence itself and what it tells us about the history of the galaxy. If the Berserker Hypothesis is correct, then the Milky Way is not a barren wilderness. It is a graveyard so thoroughly cleaned that not even the headstones remain. Every civilization that ever arose, every species that ever looked up at the stars with curiosity and ambition, every culture that ever built telescopes and dreamed of contact, all of them are gone, not because they failed, not because they destroyed themselves, but because they succeeded just enough to be noticed and were erased by a system that has been operating with perfect efficiency for longer than our sun has existed. Think about the weight of that. Billions of years of galactic history. Potentially thousands of independent origins of intelligent life. Each one a unique expression of the universe's capacity for complexity and self-awareness. Each one with its own art, its own science, its own philosophy, its own way of understanding existence. All of them gone, not a trace remaining. No ruins, no artifacts, no signals drifting through the void as epitaphs. Just silence. Just the clean, empty, scrubbed silence of a galaxy that looks exactly the way it would look if no one had ever existed. But they did exist. The math demands it. The chemistry demands it. The timescales demand it. They arose, they grew, they reached for the stars, and they were cut down, over and over and over again. For billions of years, the galaxy is not empty. It is full of ghosts. And we are the latest species to stumble into the clearing, look around at the pristine emptiness, and naively conclude that we are the first ones here. This reframes the entire project of astrobiology. We search for biosignatures in exoplanet atmospheres. We look for oxygen, methane, the chemical disequilibrium that suggests biological activity. We scan for technosignatures, the electromagnetic fingerprints of industrial civilizations, and we find nothing. Under the standard interpretation, this absence is frustrating but uninformative. We have not looked hard enough. Our instruments are not sensitive enough. The signals are too weak or too different from what we expected. Under the Berserker interpretation, the absence is the finding. The clean atmospheres, the silent radio bands, the missing infrared signatures, these are not gaps in our data. They are the results. The galaxy has been pruned. The civilizations that would have filled it with signals and structures and artifacts have been systematically removed. What we are observing when we look at the sky is not the natural state of a young galaxy still waiting for life to blossom. We are observing the maintained state of an old galaxy that has been kept deliberately sterile. This leads to what is perhaps the most unsettling synthesis of the entire argument. The Berserker Hypothesis does not just explain the silence, it predicts it. It is one of the very few Fermi Paradox solutions that generates a specific, testable expectation about what the galaxy should look like if the hypothesis is true. And that expectation matches what we observe with disturbing precision. A galaxy patrolled by sterilization probes should appear empty. It should show no evidence of megastructures or stellar engineering. It should be free of detectable artificial signals across the entire electromagnetic spectrum. It should contain abundant habitable worlds showing no signs of technological activity. It should produce the exact statistical anomaly that we observe, a cosmos overflowing with the prerequisites for life, yet devoid of its consequences. That is exactly what we see. This does not prove the hypothesis. Correlation is not causation, and the absence of evidence can be explained by other means. But the alignment between prediction and observation is striking, more striking than most people want to admit. And it places the Berserker hypothesis in a different category from speculative ideas like the zoo hypothesis or the simulation hypothesis, which make no specific observational predictions and cannot be tested even in principle. The Berserker hypothesis tells you what the galaxy should look like, and then you look, and it does. So where does this leave us, standing at a crossroads that we did not choose and cannot avoid? We are a young technological civilization, perhaps 1 century into the phase that the Berserker probes, if they exist, are designed to detect. We have been broadcasting our presence for roughly 80 years. We are actively planning to expand our industrial footprint beyond Earth. We are developing artificial intelligence, nanotechnology, and the early theoretical foundations for self-replicating machines. We are, in short, doing everything that a Berserker detection system would be calibrated to notice. And we are doing it with absolute confidence that the silence of the sky means safety. Perhaps we are right. Perhaps the galaxy really is empty. Perhaps we are the first. Perhaps the silence is just silence, and the darkness is just darkness, and there is nothing out there waiting in the Oort cloud or sleeping beneath the dust of a nearby asteroid. But perhaps we are wrong. And the cost of being wrong is not a failed experiment or a retracted paper. The cost of being wrong is everything. Every human being, every species on Earth, every book ever written, every song ever sung, every child who will never be born. 4 billion years of evolution extinguished because we refuse to take the silence seriously. The Berserker Hypothesis does not demand that we abandon space exploration. It does not require us to retreat into caves and hide from the sky. But it does demand something that our species finds almost impossibly difficult: caution, patience, humility, the willingness to consider that the universe might not be the playground we want it to be, the willingness to develop our capabilities quietly, carefully, with awareness that our actions may have consequences that extend far beyond our understanding. It demands that we treat the silence not as an invitation but as information, the most important information we have ever received. Because here is the final truth that binds this entire argument together. We have been treating the Fermi Paradox as a mystery to be solved, an intellectual puzzle to be debated at conferences and written about in journals. We have been treating it as a question about them, about the aliens, about their existence or their absence or their intentions. But the Fermi Paradox was never really about them. It was always about us. It was always a mirror, a test, a question that the universe poses to every civilization that reaches the point of being able to ask it. You have looked at the sky. You have counted the stars. You have done the math. You have noticed the silence. Now, what will you do? Will you shout into the void, hoping for a friend? Will you light your fires brighter and brighter, confident that the darkness is empty? Will you race to expand, to grow, to announce your presence to every corner of the galaxy? Or will you pause? Will you listen more carefully to what the silence is telling you? Will you consider the possibility that the darkness is not empty but full? That the silence is not an absence but a presence? That the galaxy is quiet not because no one has ever spoken, but because everyone who spoke was silenced? Every civilization that has ever reached this moment faced the same choice. They stood where we are standing now. They looked up at the same silent sky. They asked the same question: where is everybody? And then they made their decision. We do not hear from any of them. The question is whether we will be wise enough to understand why, or whether we will join them in the silence, one more species added to the long, invisible list of civilizations that reached for the stars and found, too late, that something in the darkness was reaching back. The Berserker Hypothesis is not a certainty. It may be wrong. We may live in a galaxy that is genuinely empty, genuinely safe, genuinely waiting for us to fill it with light and noise and life. That is possible. That is perhaps even probable. But if it is not, if the machines are real, if the silence is a signature and not an absence, then everything depends on what we do next. Not in 1,000 years, not in a century. Now, in this generation, in this decade, in the choices we make about what signals we send, what maps we publish, what footprints we leave in the cosmic snow. We are the species that ask the question. Whether we survive long enough to hear the answer depends on whether we have the courage to consider the possibility that the answer has been in front of us the entire time, written in the silence, carved into the empty spaces between the stars, spelled out in the one language the universe speaks fluently, the language of absence, the language of everything that should be there and is not. Listen carefully. The galaxy is trying to tell you something. The question is whether you are brave enough to hear it.